Welcome, SOS 232, folks. Hopefully, you're doing well. Hopefully, I haven't overwhelmed you too much with Module 4, Module 5. I know it's a lot, but we're nearing the finish line. We only have a couple modules left, and really, this is the last big one. So, buckle up. You got this. Deep breaths. We're going to cover a lot of things that are going to involve probably some of the more mathier things. And I'm going to say this, it's more mathier in the sense that you need a pocket calculator. You can use your cell phone. That level of calculator will be good enough where you have to add some numbers together. Beyond that, that's all you really need to know. We're going to go through some things involving some lines and plotting dots, coordinates. It's very basic. It's very, if you are blanking on your days of algebra, you're fine. But I'm giving you that heads up to be ready. Take that deep breath. Let the math anxiety flow out of you. And we're going to talk about these things in terms of concepts and also bring this stuff to life in what is the last big module, regression analysis. We're going to go into module 6, basically tiptoeing into regression. We're not going to go heavy duty. We're going to go very basic and just talk about these things. We're going to talk about some statistical significance, also the practical significance. And these are things that I know that you all can do because we're not going to go too heavy into it, but we're going to talk about analyzing it and what those things mean and how to determine whether we have good relationships between two variables. We'll talk about some things, scatterplots, correlation, regression statistics. It's going to be a little bit mathier than usual, but we're going to focus more on the images, tables for this module. Remember that you got this. Don't overwhelm yourself. It's a good sort of rule of life, but also a good rule for this module as well as social stats as well. Go through these steps. Even if you're going at 2 times speed, watch through it because it'll make sure that you do well going forward alongside the rules of writing, the additional problem, etc., etc., etc. Do those things to make sure that you're good to go. Now, the outline for this module will be comparing in general two quantitative variables, two numerical variables. So instead of categories, we have, like we did with chi-square, or a categorical and a numerical variable, where we dealt with ANOVA. We're actually going to go through and use a regression type analysis. But this is comparing these two things, how they differ from previous work, and then going into scatterplots and correlation to sort of discuss how these relationships can be understood from even just a descriptive point of view. So we did descriptive statistics back in module 2, module 3. We're going to go back and talk about that a little bit now with two variables when we talk about regression. But we're also going to go through and making this sort of regression model, talk about what models really are, how they differ from things like formulas specifically, and then also talk about making these lines, these linear relationships, reporting the specific values that are involved with it, doing some interpretation of the specific tests, and talk about something that's called R squared, this coefficient of determination. It sounds really complicated. It sounds a little bit terrifying. Honestly, if I look at this is like blah, 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 blah. But we're going to break this down. So come on, enjoy the ride. Don't let yourself get overwhelmed with this. Okay? Let's do this. Oh, as always, write things up. All right. So what we've done so far. Over the past couple modules, we sort of explored how they compare relationships between two categorical variables with chi-square. Then we have a categorical variable and a numerical variable, and we use ANOVA. And I mentioned before that we sort of go a little sneaky with it, where really ANOVA is better when we have a categorical variable trying to explain a numerical variable. But since we're really just talking about relationships, we're not trying to find any sort of cause and effect relationship because we have these social surveys, they're more pattern recognition. we are going to focus more on, these associations, and associations can go back and forth. If X is associated with Y, then Y is associated with X. Nothing about causation, just the patterns are matching. So now we want to start to examine how to deal with relationships. There are two numerical variables. They're now both on this sort of numerical, continuous, often scale, and we want to look on how we can bunch them together. And it really gets bunched together in a term that's called regression analysis. It sounds complicated if you did psychology. It's not the same sort of like past life regression, but like, or regressing down to the fetal position as you're freaking out. Don't freak out. But it deals with the idea of figuring out how to take one variable and see how it's connected to the others. So, again, in relationships, we've done the chi-square, we've done regular ANOVA, and now we're going to do the regression analysis, which actually involves another type of ANOVA. We'll talk about that too. Now, what the heck is regression analysis? It's a fancy stats term. Yes, we get a lot of fancy stats terms, but this one talks about how to use our data to make a model of how we think two or more variables will respond to each other, specifically one variable to the rest of them. We have an explanatory or independent or predictor X variable that often tries to explain another variable, this dependent Y variable, and how it behaves the way that it does. Now, this statistical modeling concept could be an entire course, and in some cases, it could be an entire degree program on its own. There is so much importance to the idea of trying to make these models. If you go into, especially if you're going into something that's public health related, or if you're going, or any sort of health related, you definitely start seeing these models more over. In statistics, and into even social science research and sociology, we don't do it a lot, and that's why it's sort of pushed to the end. But this concept really is the bread and butter of what you might start seeing going further. And it's where we're seeing a lot of advances being pushed into the idea of how can we model better and fit all the key elements we're looking for. Now, I'll only begin with the foundations and how to just compare two numerical variables. There's a lot of technical things that could be done. If you're really, really interested in this stuff, I recommend looking into maybe a stats course. If you really do the pain and suffering, go into a stats department course and ask about regression in that framework. There's often higher level stats courses. I think you might need a statsy stats course before trying that. But ones that deal with those models, that regression analysis, it's its own sort of thing, and it's really neat. This module kind of just talks about it, brings it to the surface, and lets it bubble over enough so you feel like, oh, I'm in the water, I feel warm, I feel like I can analyze a little bit. And we're going to do that through three major components. One, through the idea of scatterplots, because I like to do visuals. I'm a visual person. And so I like having the scatter plot because it's a plot, it's a graph. A graph helps tell a story. We're also going to look at something called correlation. In a lot of those terms, correlation is like this fancy term that is often used and often misused. And we're going to talk about that a little bit too. And then we're going to talk about the linear regression line or a regression line. And we're going to see how important that can be used in explaining how these relationships may exist. The first thing we're going to talk about is scatter plots, and I'm going to give you a warning. I'm probably going to dial down the warnings a little bit more going further, but there's going to be some math ahead. Again, don't let it freak you out. Don't give in to that anxiety in this moment because That's it. All of you all have seen this at some point. You may have blocked it out, ran over it with other memories that feel more important, warm and fuzzy memories that don't involve math. But you've seen this stuff before. We're just going to talk about it a little bit more and then actually kind of see, in my opinion, what's kind of cool is like actually getting to see why did you learn it in the first place? And this is kind of where those lines really do make a big picture and big story. Now, if we have two quantitative variables, we can actually visualize this stuff a lot easier than maybe some of the other visuals I showed you all. Such visuals that take bivariate data, or the data with two variables, the coordinates. Basically, you can treat it like, in algebra, we had that coordinate plane of the XY axes. Or you can even think of it as basic as Battleship. If you played the game Battleship before, there's certain coordinates, and if you get all of them, you sunk my battleship. That type of game. These ideas of coordinates just basically find like even longitudinal and latitudinal situations. You find those 2 points and you see where they meet, and that's the crosshairs of it all. But these visuals that incorporate these elements of bivariate data are known as scatterplots. These plots basically will place the y variable on the vertical axis, go up and down. And then you'll take the x variable and it'll go left to right. And we'll say, all right, we'll take these these pairs of variables, and x is 28, y is 20. We'll treat this as what we call a coordinate point. We'll find 28 on the x, and we'll find 20 on the y, and that will be the coordinate point that we'll plot it as. And we have a coordinate point found right here. That's all you got to do. Am I going to ask you to do this by hand? No. Are we going to use Jamovi? Yeah. But to see this stuff, we'll talk about a little bit so that when I start jumping into it, you don't feel like I'm just going into completely new territory. It's just maybe a little fuzzy. But this, when you put them all together, becomes this sort of scatter plot graph. And so when we get a graph that looks kind of like this, we can actually start exploring the narrative behind it. There are properties, there are things about it that we can talk about. And those components are actually kind of what helps really explain where the patterns exist and how we can incorporate them into the way we describe things. The other, things like ANOVA and chi-square, it's a little bit trickier to describe those things. I kind of, wave my hands. This actually gives us a better way to describe things. And so we'll do so through the idea of form, the idea of direction, and then the idea of strength. The form is the easiest. It's kind of saying what kind of shape, just like we talked about shapes of maybe a histogram, if it looks like a big lump or it's really skewed or whatever, those are forms as well, and explains the shape that appears in the scatter plot. In this class, we're going to focus mainly on straight lines. And then really, if I look at the data, yeah, it looks like I have, a bunch of lines going up and down. But if I were to look at it, it seems to follow kind of like this sort of linear path. Maybe there's a little bit of curve, but for the most part, it fits a good linear path to it. And so in this course, and we don't have to worry about things being, a perfect fit, but a decent fit, or at least a good idea. If I were to say it looks kind of like a straight line going downward, if you have more absences, your grade goes down. That tells me that story pretty easily. But note that, and we'll talk about it very briefly, but like note that we'll focus mainly on the straight lines. But there's more relationships could be made. Curves and others, it's a little more advanced. If we had more time, talk about it, but we don't. We're going to focus on this and make sure that you feel comfortable with the straight line relationships for these two quantitative variables. Now, we talk about, line. Well, what kind of line is it? The next step to figure out what kind of line it is sort of looking at the direction of the line. We usually describe it, we talk about a linear or straight line relationship. So going back to how a school algebra, I know, trigger warning. Not too far though. We can just talk about a slope of a line. Basically, a positive slope goes, sort of uphill. A negative slope will go downhill, and horizontal is really when there's no slope or a slope is zero, where it almost looks like a flat line. Just how a line will have a positive and negative slope or no slope at all, we could have three types of what we call linear relationships. We can have a positive linear relationship. A positive linear relationship is basically as the x variable goes up, so does the y. Height and weight probably are one of those things. The taller someone is, the more likely, the more that they would weigh. Negative linear relationships suggest that as one variable goes up, actually the y goes in the other direction, y goes down, and vice versa. So, a easy way to understand that is trying to talk about as as your sleep schedule. If you sleep less and less, your reaction times, your cognitive abilities will go down. So if you see people who are sleeping more, if you get more rest, then those hiccups, those problems will actually start dwindling. So you'll actually have better cognitive abilities. But if you if you get more and more tired, if you stay up longer, so the longer you stay up every day, so if you go from being awake 16 hours to 24 hours, maybe from 16 hours onward, as that goes up, then your cognitive reflexibility, your reaction times, all those things will go down, and that sort of goes into a negative relationship. No linear relationship. I'm going to be very specific. There's just no line that really makes sense. It's not saying it's not a relationship. We're going to talk about that soon. But that whatever, if there is one, it's not a linear one. It's got to be something else. So let's try some examples, get comfortable. Let's look how, the variable income in thousands of dollars could be compared to maybe my variable of life expectancy, maybe, or how many years one expected to live in a country or an area. If the area gets richer as X increases, it looks like you're expected to live longer. Y also increases. You can sort of make an arrow and see it goes in sort of upward trajectory. As X goes up, so does Y. Since y also increases when x increases, we can say there's a positive linear relationship between these two variables. If I want to look at maybe something, a little bit more scientific, but not too much, elevation. If I go higher and higher above sea level, the mean annual temperature, this is in Celsius, you could still do it in Fahrenheit if you wanted to, as x increases, that temperature actually goes down because less atmosphere, so it gets a little bit colder. That's why you see snow in the mountaintops and whatnot. Since y will decrease when x increases, there's a negative linear relationship happening between these two variables. Now, the situation I have here, amount of chocolate eaten in daily in ounces, and the days of school missed. It's a mess. This data is all over the place. I see no connections whatsoever, which means you could eat your heart's consent of chocolate or maybe sugar-free chocolate or something. And I shouldn't expect you to miss more days or fewer days. There doesn't seem to be a connection between the two variables. And with such scattered data, it's probably wise just to say there's no linear association going on there. There's no linear relationship that we can claim. Now, just because we have no linear relationship doesn't mean that a relationship doesn't exist at all. Consider the scatter plot below. So maybe we go sciencey, where we look at speed to fuel data. If we try to In this situation, if I try to fit a straight line to it, it probably looks something like this. Just basically my experiences. And this claims there's no line linear relationship. I don't see anything here, but like this doesn't seem to fit the data very well at all. In fact, if I go from 0 kilometers an hour to 60, it looks like actually this sort of fuel used will go down. And in fact, if you're speeding up because there's less requirement to you know, accelerate, it gets it to a point where it's easier to just get once the inertia is in motion, the car is just easier to run. And so it runs less gas when you're at that sort of staying at 40 or 60 kilometers an hour, basically 40 miles an hour roughly. But once you get past that point, then it's starting to having to need more gas to stay fast. And that and it uses more gas and uses more fuel in liters as it keeps going up. So in this situation, I think there's a pretty clear relationship going on. It's not linear. I don't think a straight line makes sense. But in this case, it does look like a curved relationship, curvilinear, parable, parabola could even be considered. These curved relationships still say that there's a relationship, but we just don't claim it's a line. The last component we're going to talk about, so I talked about some forms, I talked about the direction. Now let's talk about the strength of the relationship. This association observes how closely the association follows this pattern. In the scatter plot here, the data seems to follow the pattern of the line pretty easily. Not too terribly, there might be a little bump here and there, but for the most part, it fits it nicely. It doesn't have to be perfect. That's okay. We'll talk about why it doesn't have to be perfect in the next few slides. But we don't need that perfection. We just need to see a good understanding about where it seems to fall alongside of a line. Now, I want to do more than just looking at something. How are some other ways to analyze it? There are a bunch of ways to be very honest about it. We're going to cover a few of them. We're going to focus on, when we focus on measuring something numerically, one of the ways we can do so is what's called the correlation coefficient, or R. This is a way to measure numerically how much of a relationship and how strong of a relationship do we seem to have. For sample data, the linear correlation coefficient R, sometimes written as a little r, numerically measures how strong the relationship between two variables x and y actually are. The statistic also measures how x and y will vary together compared to how they vary on their own each. So what I'm basically saying is like how x varies whenever y changes, that has its own measure. And so if we take that amount of, x varies, y varies a certain way, and then sort of standardize it to how much x varies just in its own right and y varies in its own right, the correlation coefficient numerically measures that. Some facts about the correlation coefficient are a positive R indicates a positive association between variables, while a negative R indicates a negative association. Now, these associations are just not any old associations. They're linear, straight line relationships. So if you get a scatter plot and you see something that doesn't look like a straight line relationship, it looks maybe like a curved relationship, I wouldn't recommend using the correlation coefficient. We'll talk about other ones we can use, things like R squared eventually. But right now, if we don't have a straight line relationship, don't use don't use R, don't use the correlation coefficient because it doesn't really work really well. It's not intended for that. R will always be between -1 and +1. It's stuck between there. It's almost like perfect is 1 on perfect positive, and a perfect negative, the extreme value of -1, basically indicate these perfect straight line relationships. R equals 1, a positive, perfect. As x changes, y changes in the same whatever respective variability, and they sort of go hand in hand. Now, is that going to happen in real life? Not really. We know that for the most part, there may be certain formulas that we follow, but like not everything just follows as planned. There's going to be that deviation, how things sort of go off the beaten path. And so We don't expect the R to be those negative one, positive ones, but that's as far as you're ever going to get. The correlation will stay the same, even if you switch the variable x, which variable is x and which variable is y. So there might be cases where you're not sure. Which one do you think should maybe explain the other? Or you choose one of them. Did I do it wrong? No, because the correlation will actually stay the same no matter which one way you're trying to test this stuff or which way you try to claim the y variable and the x variable. It switches it, same idea. It's like association. If there are outliers in the data, it can affect R quite a bit. And this is something that I talked about a little bit prior. Correlation only makes sense for quantitative variables. When I look at these sort of how these things are varying, it actually has a lot to do with, in the background, some standard deviation that only works for the numerical variables. So these quantitative numerical variables, that's only where a correlation actually, you know, but actually, or well, actually, that's where that makes sense. You can talk about associations between gender voters and political party, but not the correlation between them. Because, like, what do you mean as one goes up? Are you saying that women are better than men, men better than women, or etc.? That doesn't make sense because this whole ranking isn't legitimate. They're just categories, they're groups. So you can talk about an association, the relationship between them, but not a correlation because we don't really have that sort of ordering that comes from these quantitative variables. So height and weight, that can have a correlation. The other, when you have a categorical variable thrown into the mix, not so much. So some examples being a perfect linear correlation, a very strong one when r is equal to 0.9, as well as -1 and -0.9. We see it's basically almost the same thing, only in the other direction. A weak positive linear correlation is when it's equal to 0.1, maybe, and it's kind of all over the place. There's not a lot of connections here, as well as in the other direction of -0.1. We could have just the whole blob of nothing. And that would mean it's linearly uncorrelated, no linear correlation, probably no relationship whatsoever, anyways. But we also have part H, where it says no linear correlation, they're linearly uncorrelated. But this starts to look like a curve. I think this is a curved relationship, and that's something to keep in mind that I could still get R, this correlation coefficient, being 0, but it doesn't mean there isn't a relationship. Like a p-value, there's actually no official cutoff what a good correlation coefficient is. We might have certain standards and we sort of set those cutoff points. And for introduction for you all, we kind of give those things as sort of great guidance to let you all have that ability to sort of build your gut. And then you go from there. You start looking at literature reviews, seeing what they claim, look into the argument, the assessment of these things. And there's some really fascinating articles that sort of even talk about things in social sciences way differently than what you might talk about in in the natural sciences or physics or something. Social sciences have their own sort of uh, viewpoint on things. We'll talk about that a little bit more, but like just keep that in mind. So based on the previous photo, the closer the value R is to either 1 or -1, the stronger that correlation, that relationship would be. So ideally, we want them to be really as far away from 0 in either direction as possible, because that suggests that we have a strong relationship. But a good rule of thumb, if I'm getting values between about -0.3 to +0.3, this is a weak linear relationship. There's not a lot going on there. So we want something typically beyond 3/10 in either direction. If it's between about 3/10 and 7/10, either -0.3 to -0.7 or +0.3 to +0.7, we have a fairly moderately strong, generally okay linear relationship. And in social sciences, that might actually be amazing because people are are varied. But if we can get something that's between zero point 0.7 and 1, oh, that's amazing. That's really showing that there's a major relationship happening there. That, not everything's perfect, but it's pretty darn good considering all the different mechanics of the universe that could be applying to these things. Ideally, we want a linear relationship that's moderate or strong. That's our goal. There's some hiccups. Like I said, I sort of eased into it. There's hiccups with social science data. Many of the examples we explored so far haven't really done survey research. With social science data, the scatterplots and corresponding relationships may be a lot harder to pinpoint since we're dealing with human beings. Humans are all kinds of varied. We are unique creatures of havoc sometimes, but we also have a lot of variance in the way our behaviors are. To try to predict for the human condition could get really tricky. With social survey data, we're not actually setting experiments, we're not controlling for anything. Those relationships may not be exceptionally strong. The scatter plots may also look really weird. So something like this for education and family income. This doesn't look like those nicer scatter plots I kind of gave you all prior. That's okay. Social science research has its own sort of havoc when it comes to some scatter plots for some of our survey results. Many researchers have written papers exploring the situation. And often, if we seem to have a correlation of R that's higher than 0.3 or lower than negative 0.3, so like I said, that moderate or strong situation, we'll take it as a win. We'll say it's good enough that there is some sort of relationship going on, and we won't overthink it. There are also cases where even less could be considered acceptable in some capacity. That's something to not overthink. That's an argument that goes well beyond this course. But yeah, in this class, if I get above 0.3 in social survey data, I'm happy with it. I will take it. I will make a claim that there's something going on here in the wide scope of how varied the human race can be. So make sure to review the Jamovi short video on how to do a scatter plot and do the following rules, placing your independent explanatory variable, and the one that's predicting on your x-axis, the dependent variable, usually consider a response variable on the y-axis, and make sure to include the linear option for regression line so others can view the line of best fit. It's a great reminder, caution, association, or correlation does not mean causation. We will find patterns and, knock on wood, we're going to be able to, see those relationships pretty nicely, but it doesn't mean one thing is causing the other. I used to think correlation implied causation. Then I took a stats class. No, I don't. Sounds like the class helped. Well, maybe. Cheesy joke on the idea that there's a pattern, there's a relationship. I can't claim that it causes it. But sometimes logic does prevail. All right. Talked about a lot of concepts, introduced you to a lot of things. Take that short break, take that breather. Before going forward, feel free to test your knowledge on what you've learned so far. Run through these things, some examples. All right, ready? Next piece. In the previous slides, we explored our scatter plots and correlations between two quantitative variables, x and y. So now we're going to look at an outline of our linear relationships we're dealing with. If our correlation R suggests that a linear relationship is present, then it makes sense we got to know what kind of line of best fit, or basically, what kind of line do we have? That's going to be the goal for the next few slides. We'll try to fit the best possible line through the points so we can predict the value of y for a particular value of x. Prediction is really one of the key components of the statistical modeling game. This area of statistics, we try to make a model that explains why a variable y behaves the way that it does. over for a second. So I'll give you a small math reminder about lines. Another math class flashback. I apologize for the anxieties. Deep breaths. We got this. Back in high school algebra, you learned about lines. Probably even did it in geometry as well. These lines usually consisted of two properties, in an algebra sense at least. If known, tells us how to make the line. If we know the slope and if we know the intercept, we are good to go. The slope and the intercept can actually be made a line of the slope intercept form. Y equals mx plus b. And you can always solve for y for then just plugging in x. So our graph to our right, our slope is actually -2. And our intercept is 1. By plugging into these two values, we have put it in slope intercept form if I needed to. And then if I say when x is 3, we can solve for y by just plugging in 3. -2 times 3 is -6, plus 1 is -5. If you need to use a calculator on this, do it. This isn't trying to have you do the numerical stuff in your head for extra credit points. If you need to use a calculator, I'm here for it. I totally recommend it. It's not worth not doing. All right, let's extend further. In math and science classes, you also have used formulas. Now, formulas are more deterministic. In a formula sense, just like the conversion from Celsius to Fahrenheit or inches to feet, these formulas are more deterministic. You just plug in your needed values, and the formula outputs the same answer every time if your input is always the same. So if I say there's 4 quarters and $1, a formula to figure out how many quarters there are in D dollars would then just be number of quarters is equal to 4 times the number of dollars. So if I have $5, there's 4 quarters of the dollar. 4 times 5 is 20. That means you get 20 quarters for $5. Models actually incorporate formulas as well, but they go further. They allow you to say, oh, I have an idea what this should look like, but it doesn't always have to be perfect. I can be something that fits really well, but allows there to be a little bit of an offshoot, something that goes a little bit further away, or we'll eventually call it an error. How far or where it's differing from where we expect it to be. These models allow for error. So it has this sort of deterministic formula component, but it also has this error component that we can merge together to model stuff and saying that it should fit this for the most part, but we may be off a little bit, but the pattern's still there. Formulas don't really allow for error. It says it has to be one thing, you input, you get the output. Models actually are more like real life because with different inputs might produce different outputs. Basically, because life is, to quote Jurassic Park, life finds a way. And the line of best fit, or the regression line, then comes into place. Let's see. Yeah, line of best fit. There we go. Now it's perfectly okay to have some error, but we don't want to do it too much. We want to make that error as small as we can, since we want to get as close to the real values as possible. We accept that real life has a little bit of wiggle room to it because not everything's gonna be perfect, but we still want to try to get as close to perfection as possible. Now, we don't have the entire population, so we need to estimate this line using survey sample data that we have. We typically won't have a full population. We're going to have our sample data or our survey data that we can gather, but it's not going to be everybody. So all these things are still going to be estimates, just like how we might have a sample mean, a sample proportion. We're also going to have a sample line. This best fitting line that estimates how y relates to x is then known as your least squares regression line. And this line actually is the best one based on this criteria. There are mathematical, theoretical formulas that say, based on the numbers you come in with, This is the line that will do the best at reducing the amount of error based on a complex math formula given the data we got. We will call something called y hat to be the estimated y value. And I'm going to use this interchangeably. I will have this little y with this little arrow on top, this little hat on top, or I might just call it y hat. In this class, that can be interchangeable. I don't mind. I need you to do both one of them for credit and so on. But beyond that, I don't require you because I don't need you to do fancy Microsoft Word equation editors to tell me what's going on. But it's basically considered the estimated y value. Whenever you see hats, it's usually this is estimated by our data. And the regression equation then becomes also this equation, the regression line. It's written as this y hat is equal to ax plus b. So instead of calling it mx plus b in the slope-intercept form, I try to keep with like the letters of the alphabet, a, b, and so on. But a will be your considered slope. Well, b is what we're going to estimate to be the intercept. So slope-intercept form, same idea, slope and intercept. Both these values are estimated from our sample data. Other classes might write this differently. If I taught a different version, a stats for majors course, I think stats 270 at EKU, I would write it differently. I would talk about it differently. But the ideas are still the same. And so in this SOS 232 class, I kind of expect you all to write it like this and call it A and B for your slope and intercept if necessary. The only thing I will let you get away with is instead of having to put that little caret arrow thing on top, if you write it y dash hat, I'm okay with that. I'm not going to be too worried because I don't see it as a huge deal because you're still telling me that you know what's essentially going on. This is the estimated, the predicting y as opposed to the real one. The properties about this sort of y hat is equal to ax plus b. The estimated slope, a, is the average change, increase or decrease in y when x actually goes up by 1. Same idea, if you had slope in high school. As x goes up by 1, how much should the rate of change does y go up or go down? The estimated intercept is of the regression line, usually in this case, b, is the value of when x is 0. It's when x crosses that sort of intercept itself, when it crosses the y-axis. It's not very useful typically. And the real reason I don't talk about it too much, I didn't want to do so far in depth, is that when you're dealing with your data, you really want to stay within the range of x's that you have. So often the case, you don't have x values near 0. So that's where it's not as much useful. To make predictions, you just substitute an x value into the equation and to find y hat. So interpreting the slope, making predictions, those are the big pieces of the puzzle that are really nice for the regression line. So say we wanted to predict a student's grade based on the number of absences they had in a term. Well, X be the number of absences, Y be their course grade. And based on this data, computer found the regression line to be Y hat is equal to negative 7.093X plus 101.344. Don't get overwhelmed. All this is saying is the same thing in this picture is also helping guide. This is why the scatter plot's great. Miss more classes, grade goes bye-bye. Your grade goes down. It decreases. And it decreases by about 7% every time you miss a class, on average, according to this course. So if I wanted to interpret the slope, officially, I would say for every additional absence, or as the absences go up by 1, we expect a student's score to decrease on average by 7.093%. So note, I'm using this 9.3%. Where the percent come from? That's your grade. Grades are percentages. So think about these things in terms of units when you're involving it. You can also predict that when x is 4, when there's 4 absences, y, use a calculator, highly recommend, y hat becomes 72.927. So students who miss 4 classes on average made a 72.927%, or basically a C in this class. This is probably one of those weekly night classes. So if you're missing 4 of them, you're missing an entire month of class. And maybe grades are a little bit rockier because of that. So the slope, some extra notes, the slope is always going to be in the direction of the linear relationship. So if it's a positive linear relationship, the slope better be positive. We have a negative relationship that's linear, then A is going to be negative as well. It's going to be less than 0. Interpreting the slope is the important part. The intercept, we can sometimes get away with it. There's other cases we won't focus on it. But it's a bit of a cookie cutter format. Y decreases when A is bigger than 0, or increases when A is bigger than 0, Y decreases when A is less than 0. Other than that, it's like for every additional, whatever your X variable, includes your units, we expect that the Y variable will either increase or decrease, depending on that A value, depending on your slope, on average by the actual value of the slope. That's all you have to do. You just fill in the blanks, fill in the gaps when you're talking about it. Predicting may require a calculator. I'm not going to pretend to do all this stuff in my head. I use a calculator because I don't want to do it in my head. It's a lot of work. But interpreting it is pretty easy once you find what that y hat is supposed to be. People who missed X, and talk about the unit of X, so X days of class on average, had y hat prediction in your unit. So basically, had about a 73% in the class. Same sort of cookie cutter stuff as before. Now, using Jamovi to get a regression equation, we're gonna, how do I get these numbers? You're not doing it by hand, not this course. You're gonna use Jamovi. You have to identify the values for the slope and the intercept in order to make the regression equation y hat equals ax plus b. You'll be shown how to do these results soon, but let's talk about it very briefly and focus on these values to make a regression line. So you're going to get this table that says model coefficients, real length, that's our y variable. Predictors, intercept, and this EDOC. It's education, number of years of education. That's actually our slope. The estimate column is going to actually give you your values for your estimated slope intercept. The intercept's always going to be that first row. Da, 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 intercept, not a shocker. Slope is always going to be the second row in one of these simple linear regression models because it's basically the other one. It's saying, how much should this change? And based on these results, I can plug into the regression model, the regression equation, that line based on this data would say that y hat is equal to 5,168 x minus 36,133. And all I did was just take those numbers, plugged in for A, plugged in for B and did y hat equals to. That's all you have to do. And gives you the regression equation that estimates what we think the line should be. All right. Again, a lot of concepts. Take that breathing room. Try some of the practice questions. Feel like you get comfortable. And once you feel at that level, we're going to go into how can I evaluate these relationships looking at through statistical significance like we did before, as well as practical significance. So some new tools, but the same ideas. Don't feel too overwhelmed, hopefully. Take that break. Take the breather. Good deal. So let's take that some ways to evaluate the significance. We'll explore the statistical significance, the ANOVA F test. But this is slightly different when we're working with regression. We might call it the regression F test or regression ANOVA F test. This is a slightly different test. It still actually uses ANOVA, but it's a different type of ANOVA. It's dealing with these different types literally, but that's more of a mathematical determination. If you want to go more, take those stats heavy math classes, but just know that it's similar but a little bit different. Cousins. To examine practical differences, practical significance, we're actually going to use another formal statistic that measures how good the model is explaining how our y variable varies. This measure is known as the coefficient of variation, also known as r squared. We're going to use that alongside correlation to help explain the whole thing that's going to be going through. And to repeat, what we talked about before, these tests of statistical significance allow us to determine whether our findings are generalizable to the population. Is there a reason to believe the population actually fits this sort of hypothesis? How confident can we be that the relationships we are observing in our sample data reflect something broader and generalizable to the population? That is a big deal. Go back to module 4, see how we talked about those things, because without being able to generalize the population, we're just playing around. We're not actually doing anything that's helping society. We want to generalize to a bigger population based on the data we collected. So regression ANOVA F-test definition. The regression ANOVA F-test of statistical significance is subsequently used when the data is represented the population under investigation, and that's when we have two numerical variables. This is different than we did before. We had the one categorical and one numerical. Now we have two numerical. Now, I won't say this too loudly. You can actually do this regression. This regression ANOVA is the one that kind of catches all in its own stuff. It gets more nuance. It's beyond the scope of this course, but this one is arguably the better one. But when using two continuous variables and testing the relationship between those two variables, we can use the regression ANOVA test to determine whether or not we can be confident in generalizing the findings we observed to the data population as a whole. The regression ANOVA is calculated by using further computations of the regression line between two numerical variables. So the formulas that sort of fit these for the regression model, it's the same idea of these sums and squares, just a little bit differently described compared to the previous module. This ANOVA talks about how much basically variability is in the made by regression, how much is just random error, and how much is in the y variable. And it basically says the F statistic that's computed becomes basically the average variability explained by the regression compared to the average variability explained by the error. For our purposes, we won't worry about calculating these by hand. It's too much, and we don't have a lot of time. So I want to make sure that you see this stuff, you can do it. And if you want to spend more time on it, go take one of those stats of your classes. You will do it all right. Quick reminders, the ideas of significances, we usually use 3. The standard we're going to be using is 5%. Basically, if there's no relationship that existed, this data collection thing we did, we could have been unlucky about 5% of the time, and we would have collected data that accidentally showed relationships when there are ones that don't exist based on the criteria that we hold up. Basically, convicting an innocent person wrong 5% of the time. We don't want to do that often. That's why we want the significance level, basically our error, the chances for error, to be pretty low. And our p-value that we use to evaluate it, we want it to be no higher than 0.505, but actually a lot lower than 0.05. There's also 1% and 10%. I'll skim over it. Go back to the last couple of modules. I explained it more rigorously. We're also now going to talk about something called model adequacy, which is leading into practical significance. With regression ANOVA, we can explore whether we have statistically significant relationships existing between the x and y variables. But the really big problem is that if we have a large sample size, A large sample size actually can make it so that if the linear relationship's kind of trash, it can still be figured out as statistically significant. Because really, what statistical significant means is saying that the correlation is something other than zero. But it could be 0.02, which is a whole lot of garbage. You can't beat it. So the computation of R is only useful with the strength of association when it's a straight line relationship. If we don't have a straight line, how would we deal with that? We do so with another measure that we'll focus on that also coincides with correlation coefficient. This is called the coefficient of determination, or our R squared, which talks about the practical usefulness or the model adequacy of our regression model. The coefficient of determination, R squared, is the proportion or percent of how much a y variable varies based on its linear regression relationship with it at the x variable. R squared is also computed by Jamovi, so you don't have to do it by hand. It basically evaluates how well the regression model does to explain how the y variable actually changes things up, how it varies overall. How much of it is explained by basically what's happening with x. R squared is always between 0 and 1. It's often expressed as percentage. So one of the nice things is that it's positive or 0. It basically is the equation that fit the data. An R squared of 0 suggests the regression equation is not very useful at all. It's kind of trash. And if it's close to 1, it's really, really good. It's great. It's basically saying about 100% of the variation can be explained by just if I know how x changes. The practical interpretation of this coefficient determination R squared, 100% or whatever percentage turn it to a percent of the variation in y can be explained by the regression model using x to predict that y variable. We won't talk about too much interpreting in that way, but we'll use it to sort of make our assessments. Like the correlation coefficient, there's no exact marker for what determines what a good R squared is, but there are some rule of thumb assessments that can be made. If R squared is between about 0 and 0.1, the model is not going to be very useful. If it's between 0.1 and 0.5, it might be somewhat useful. There's a caveat. If R squared is between half and 1, we think it's really darn useful. These cutoff points aren't exact. Depending on the quality of the model we require, we might have completely different qualifying measures. The nice part with linear regression, and I didn't put it in the slides, but a good thing to keep in mind is R squared is the same, can be calculated also by taking the correlation coefficient and squaring it. So I said that 0.7 is really strong. 0.7 squared is 0.49. That's close to a half. So that's why those two coincide with each other. Likewise, I take 0.3, 3/10 square, that's 0.09. That's pretty close to 0.1. So that sort of shows between 0.1 and 0.5 is really the same as what I'm saying is between the correlation coefficient between 3/10 and 7/10. Many social science researchers, based on that idea, list that if R squared is at least 0.1 or at least 10%, this relationship can be viewed as fairly practically useful for future analysis like prediction. We recognize that it's not maybe amazing if it's close to 0.1, but that's okay because the human condition is really, really all over the place. And so if we can pick up something, we'll take it if we think it's reasonably within that sort of threshold. Now note, we're going to use a practice problem, get some examples going. Most numerical problems in the GSS are properties variables. We don't want to worry too much about the disposition variables here. They're more to sort of figure out the demographics. So we're going to use the GSS to look more closely to whether a family's yearly income, real inc, is correlated. We get to use that term now. We don't say associated or related. We actually, there's a relationship, but they're actually correlated to the number of years of formal schooling of the respondent, the EDE or the EDUC variable that we've used before when we talked about regular ANOVA last module. As always, we want to take a set time to take a setup, take our assessment, and set up our proposition. So prior examples is education level, matter, and obtaining one's position in gun control, or age matter. Now we're going to look at, does the number of years of formal schooling matter in explaining one's yearly family income, both numerical variables. We'll do similar things with small changes. Symbolic form, setting up the propositions. Real ink, is it related to number of years of education? State your hypotheses. Who's more likely, or what's Americans with more years of formal schooling are likely to have a higher family income because traditional or additional schooling often comes with additional skills and credentials that earn higher wage jobs. Makes more easy sense as a sociological argument. I'm not even using numbers here. This is my sort of practical idea when we talk about these things in those rules of writing. Always remember to use the because that's kind of where the research is doing their theorizing. Always be open to the possibility there is no relationship between the two. There could be no relationship with the number of years of formal schooling and the family's yearly income. We're not trying to, we'd like to have evidence, but we're not trying to fudge data. We're saying if it isn't there, we're not going to claim it. Again, we're going to set up our level of significance. We'll stick with 5%. If you want to change it up on your own merit, I'm not going to stop you. But if you want to stick with 5% every time, go with it. I'm here for that. Now, given they're both numerical variables, we can use the regression ANOVA f-test and use r-squared to test our relationship. In a regression form, there's certain rules in writing these things up, but it gives us a lot of information. We'll actually be able to sort of pick it apart and use a whole lot of it when we talk about assessing our data. Make sure to use the Jamovi short video. Run these things to see how this stuff all works. Jamovi, your dependent variable will be your y variable. Your x numerical variable will be your covariate. Use it to explain the y. And make sure you go to model fit and check on r squared. Those should already be there, but also check on f-test to make sure you have all those things active so it'll give you the information you need to validate these claims. All right, how do I interpret it? Let's break this down. You're going to get something like this with the ANOVA output, and you're going to have both the regression ANOVA table as well as the model coefficients estimates we're going to use as well. And we'll discuss each of these things and where it all fits. So if I want to interpret regression ANOVA results on your model's coefficient, circle the estimated value of your slope. Compare your slope value to determine whether it's supportive your hypothesis and interpret it. So do we see this positive association or do we accidentally get negative associations? So for example, in our example, we propose that Americans with more years of formal schooling are likely to have a higher family income because the additional schooling often comes with additional skills and credentials to earn higher wage jobs. I'm repeating the things I started before. I'm scaffolding this to sort of create this paper, create this narrative. We therefore expect the slope to be positive, and if I go to the model coefficients piece, and if I go to the slope, which is the second line, that's the slope that's using our x variable, which is the educ variable. And this value is positive. So yeah, it's fitting exactly what we'd expect it to be. And in fact, our hypotheses click into place. We are good. It looks, now I'm going to interpret that slope, and it looks like for every additional year of formal education, the yearly family income increases on average by $5,168. Cool. Now, if we're going to go to interpretation for the statistical significance, there's many values to read when interpreting this stuff from the ANOVA result, the regression ANOVA results. We're going to focus on first on the ones that check our statistical significance. We, just like before, we have the F statistic, which is what we're going to measure because we're using ANOVA. We'll have the degrees of freedom DF1 in this numerator of degrees of freedom. And in simple linear regression, it's always 1. It'd be different if we have something else, but that's what it is. And TF2 is known as your denominator degrees of freedom, and in this case, sort of is a good sort of measure of how large our sample is. In simple linear regression, it's actually your sample size minus two. If you go further, it gets more complicated than that. And then we have our p-value. The most important thing in there, it tells us the chances of if we were to reject the null hypothesis, say that it's statistically significant, and what are the chances of going through those motions and ending up with something like this that is wrong? There actually was a relationship to begin with. We want that thing to hopefully be low. There are rules to apply when determining statistical significance. So if we put in the parentheses, all these values, we put all four of them in there. So F is 321, degrees of freedom is 1, degrees of freedom is 1756, p-value is less than 0.001. So reported that p is less than 0.001, definitely less than 0.05, and even 0.01. So it's definitely statistically significant at the 1% level, for sure, definitely at 5%. And so we have a statistically significant relationship. Does it mean it's practical? We don't know yet. We're going to figure that out. So let's go ahead and we'll add those lines in there. So based on our linear regression analysis estimated for every additional year of formal education, yearly family income increases on average by $5,168. We talked about that before. Now we can say this linear relationship is statistically significant and give me your F-stat, your degrees of freedoms, and your p-value. It's okay to switch gears. Just like before, if I accidentally thought that it was supposed to be increasing and I saw that it was decreasing for some reason, I'll just admit to it because really all we're really focused on is trying to determine association. If we're gonna make an argument why we think this thing is, and we go in the other direction, we're still showing there's an association. It's just in the other direction. Now, there are two more values to interpret. Those are the ones we're going to be focusing for practical significance. We have the correlation coefficient R, 0.393. It's above 3/10, but still below 7/10. So I think our relationship is moderately strong. It's not amazing, but for social science, it's not bad either. We also have R squared, or coefficient of determination, the adequacy of a model, or how much of the y variable varies based on an explanation from its linear relationship to the x variable. If I had to interpret it, make sure to turn this number into a percentage. This 0.154 should be 15.4%. It is above 0.1, so we think that maybe it's not perfect, but it's still decent, and we believe the relationship between x and y has some practical significance involved there. And in social science, that might be a great accomplishment to be able to explain, no matter how wild humans can be, if we can nail that, that's rad. And there is one snag with this technique, and in another iteration, I might fix this and try to change it up with folks. On Jamovi, it only reports the positive version of these values for the correlation coefficient R. It doesn't report them as negative, even when we have a negative association. So if you see a negative linear relationship, you're going to have to go one step further when you write things up to make sure that it says negative when you write it up. For example, in this situation with education and TV hours, education, the slope is negative. In fact, we can see this line looks negative, but it reports it as a positive 0.197. When you write this up, you need to do it and put a little star, check it off, put something in the back of your head that you got to fix it when you do your write up, where you need to report it as negative 0.197. You'll need that for full credit, otherwise, you lose points for that. So, my apologies, but that is one additional thing you will have to do. So an interpretation of the practical significance basically becomes something like this moderately strong positive relationship. I'm just basically describing the correlation coefficient. Is also considered to be practically useful for further analysis. And I give R and R squared. Cool. Now, how do I put all these stuff together? That's the big picture, right? Don't get overwhelmed with these write-ups. Remember, we covered much of the results already, just bit by bit. And we're going to Frankenstein it together. And we read the upcoming paragraph, go back to the previous slides and see where each of these lines were plucked from. Also, make sure to add your scatter plot at the end with the regression line to help visualize what the data looks like. And we put them together along with our potential future scientific research. We get good results. So all I did was take everything we just talked about. Now I have it color coded to sort of see the differences. But all this stuff, this write up really just came from all the steps we just talked about. We also wish to explore whether years of formal education is correlated with family income. We propose that Americans with more years of formal education are likely to have higher family income because additional schooling often comes with additional skills and credentials to earn higher wage jobs. Based on our linear regression analysis, it estimated that every year of formal education, the yearly family income increases on average $5,168. This linear relationship is statistically significant, and in the moderately positive relationship, moderately strong positive relationship. I could have said linear relationship, but I actually said it the sentence before, so I'm cheating a little bit, being sneaky. This relationship is also considered practically useful for further analysis. And then I go back to just being a sociologist. While the 2012 data expands on the importance of formal education and family income, it doesn't describe which types of education are being pursued and how it affects the income hikes. Is it trade schools the additional year, a year in bachelor's degree? What does it mean? Furthermore, there's a question on the effects of education has changed since 2012, especially how the job market is restructured post-pandemic. Very, very sociological, but taking the data we had before. Hopefully this didn't feel too bad. Remember, review the rules of writing research for this module and all others. Carefully review the rules reporting regression and ANOVA results. Using it for the blog posts and homework. Some of you are not doing that, so make sure you do it. Also, look at the practice additional problem for reading in the reading materials for additional guidance. To learn how to get regression and ANOVA results along with the scatter plots and test for statistical significance in Jamovi, watch the short Jamovi video. And you're going to need those tools just like always. That was a bunch. And that was the last big thing. For you all who are feeling the finish line, congrats, you got through the last huge lecture. You don't have to hear my voice too much anymore after this. Take that short break, take that breather, and test your knowledge, what you've learned so far. And then go do homework, do blog posts, all those good things. That's it. Take care, folks, and good luck this week. You're almost there. Send me emails, ask questions if you have them. Otherwise, stay amazing, y'all.